Welcome. Settle in and let yourself relax. Tonight we're going to journey through time and space to witness some of the most profound events in our solar system's history, not with urgency or alarm, but with the calm perspective that 4.5 billion years of distance provides. Close your eyes if you wish. Breathe slowly. Imagine the vastness of space, the deep silence between worlds, the patient, inexorable forces that shape the ground beneath your feet, the moon above your head, the very air you're breathing right now. We're going to explore collisions, not the sudden, startling kind that make you jump, but the slow cosmic ballet of worlds meeting worlds across unimaginable spans of time. These are events measured not in seconds, but in millennia, not in explosions, but in the gradual reshaping of entire planets. You are safe here in this moment, lying comfortably as we drift back through time. The violence we'll discuss happened so long ago, so far away, that it exists now only as geology, as ancient stone, as the quiet testimony of craters worn smooth by ages of wind and rain. Let your mind wander through these stories. If you drift away, let yourself drift. There's no test tomorrow, no need to remember every detail. Just let the rhythm of deep time wash over you like waves on an ancient shore. We begin on Earth, but an Earth you wouldn't recognize. Imagine yourself standing on a shoreline 4 billion years ago. Though standing isn't quite accurate, because you couldn't exist in this world. But let your mind drift there anyway, to observe, to witness what was. The sky above you is not blue. It's a murky orange-gray, thick with volcanic aerosols and impact debris suspended in an atmosphere still finding its equilibrium. The sun, younger then, slightly dimmer, filters through this haze as a pale disk, casting everything in a perpetual twilight. The ocean before you is warm, not the pleasant warmth of a summer sea, but the deep, primordial heat of a planet still cooling from its formation. Steam rises from the surface in constant shifting veils. The water itself is a dark gray-green, rich with dissolved minerals leached from the constantly churning seabed. There are no waves as you know them, just a slow, heavy swell, as if the ocean itself is breathing. Listen to the silence. There are no birds, no insects buzzing, no rustle of leaves, because there are no trees, no plants, no life at all that you would recognize. Just the low rumble of distant volcanic activity, a sound so constant it becomes almost like silence itself. The hiss of steam, the occasional crack and groan of cooling rock, the rocks beneath your feet, if you had feet to place there, are dark basalt, sharp-edged and new. There's no soil, no sand worn smooth by ages of weathering. Every surface is recent, volcanic, worn from the planet's molten interior. The landscape is a study in blacks and grays and deep rust reds where iron oxidizes in the strange, oxygen-poor atmosphere. And above you, in that murky sky, something moves. It starts as a bright point of light, brighter than any star, growing slowly over the course of hours. This is the rhythm of this ancient world. Impacts arriving not as sudden catastrophes, but as inevitable appointments, scheduled by the mathematics of orbital mechanics. The object approaching is an asteroid, perhaps 10 kilometers across. not enormous by cosmic standards, but substantial. A mountain flying through space at tens of thousands of kilometers per hour. It's been falling toward Earth for weeks, pulled by gravity's patient insistence. As it enters the upper atmosphere, it begins to glow, not with a sudden flash, but with a gradual brightening as friction with air molecules, sparse as they are at this altitude, converts velocity into heat. The asteroid heats, its surface beginning to ablate, to boil away in a trail of vaporized rock stretching hundreds of kilometers behind it. For those final seconds, it's brighter than the sun. The murky sky lights up, shadow sharp and stark across the volcanic landscape. And then, contact. The impact doesn't sound like an explosion. It sounds like the Earth itself roaring, a deep subsonic boom that you feel in your chest, in your bones, in every cell of your imagined body. The ground ripples, literally ripples, like the surface of a pond, as seismic waves race outward at kilometers per second. Where the asteroid strikes, matter simply ceases to exist in any form you'd recognize. The kinetic energy of impact is so immense that rock behaves like liquid, like gas, like plasma. A crater forms not through excavation, but through the sheer force of energy displacing everything in its path. Molten rock fountains upward, arcing through the sky, some of it achieving enough velocity to escape Earth's gravity entirely, flung into space to orbit the sun as debris for eons. The impact plume, a column of vaporized rock, superheated steam and shattered fragments, rises into the stratosphere, then higher, spreading outward like an umbrella. For hundreds of kilometers around the impact site, the thermal pulse ignites everything ignitable, though there's precious little to burn on this lifeless world. The heat wave passes over the landscape like the breath of a furnace, and then gradually things settle. The impact plume spreads into a global dust cloud that will dim the already dim sun for months, perhaps years. The molten crater begins its slow cooling. The seismic waves circle the globe, shaking loose avalanches and triggering volcanic eruptions halfway around the world. This is one impact. One day in the late heavy bombardment. Now imagine this happening again, and again, and again. Not daily perhaps, but frequently enough that the Earth's surface is in a constant state of renewal. Large impacts every few thousand years, smaller ones monthly, tiny meteorites daily, hourly, constantly. The planet is being pounded, resurfaced, reformed by an endless rain of debris left over from the solar system's formation. Let's drift forward through time, watching this process unfold, not in human time, but in geological time, where 1,000,000 years passes like a long afternoon. The impacts follow patterns, clustering when Earth's orbit intersects with particularly dense clouds of debris. There are quieter periods, centuries or millennia, where the bombardment eases, where the surface has time to cool and stabilize. Then another cluster, another wave of destruction and renewal. Watch a crater form, its rim sharp and fresh. Watch it over the next 1,000,000 years as impacts nearby shower it with debris, as its own rim collapses inward, as volcanic activity floods its floor with new basalt. Watch as newer craters overlap it, obliterating its edges until only a faint circular depression remains. Then watch as even that is erased by subsequent impacts, by volcanism, by the slow recycling of the planet's crust. The ocean, too, is shaped by these impacts. Large asteroids striking the sea generate tsunamis that circle the globe, waves hundreds of meters high that scour coastlines and carry ocean water deep into the continental interior. The water itself is heated by impacts, sometimes locally boiled away, creating temporary scars of dry seabed that slowly refill over decades. In the quieter moments between major impacts, imagine the stillness, the slow cooling of impact melt pools, forming unique rock structures, glass beads scattered across the landscape, shocked quartz with its distinctive parallel fractures, exotic minerals formed only under the immense pressures of collision. There's a strange beauty to this world if you can step back far enough to see it. The constant renewal, the way the planet absorbs each blow and continues, its molten heart still churning, its magnetic field flickering but persistent, protecting the atmosphere from being stripped away by solar wind. Consider the chemistry happening here. Each impact brings not just destruction but delivery. Asteroids and comets carrying water, organic compounds, rare elements. The early Earth is being enriched by this bombardment, gathering the chemical ingredients that will eventually enable life. The bombardment peaks around 3.9 billion years ago, then gradually begins to ease. The solar system is cleaning itself out. Gravitational perturbations by Jupiter and Saturn flinging debris into the Sun or out of the solar system entirely. The asteroids that remain settle into more stable orbits. The rain of impacts slows from a deluge to a steady drizzle. By 3.8 billion years ago, Earth has changed. The surface is still hostile, still volcanic, still frequently impacted, but the worst is over. In the oceans, protected by water from radiation and temperature extremes, complex chemistry is occurring. Molecules are assembling themselves in increasingly elaborate patterns. Something is beginning that will, in time, transform this dead world into something extraordinary. But we're getting ahead of ourselves. Let's step back, take a breath, and consider what we've witnessed. You've spent subjective eons on this ancient Earth, watching impacts reshape the surface again and again. Think of the patience of planets, the way they endure catastrophe after catastrophe and continue, slowly evolving, gradually becoming something new. The late heavy bombardment was not a single event but an era, a long chapter in Earth's story. It lasted hundreds of millions of years, a time scale so vast that all of human history from the first cities to today would fit into it dozens of times over with room to spare. And through it all, the planet cooled. The impact slowed. The stage was being set for the next chapter. Rest now in your comfortable present, where the sky is clear and blue, where impacts are rare enough to make headlines, where the ground beneath you is stable and ancient and safe. Let the deep time we've traveled through settle over you like a blanket. There's more to explore, but for now just breathe and drift, and let yourself relax into the vast, patient time scale of planetary evolution. Let's drift back even further now, to an event so profound that every time you look up at the night sky, you're seeing its consequence hanging there, silver and silent. We're going back 4.5 billion years, to when Earth was barely 50 million years old. A cosmic infant still glowing with the heat of its formation. its surface an ocean of molten rock slowly beginning to form a thin, unstable crust. Our planet had a visitor coming. Though visitor suggests something brief, something passing through, this was more like a meeting that had been scheduled since the solar system's birth, written into the mathematics of orbital mechanics and gravitational resonance. Her name, given by scientists billions of years later, was Theia, named for the Titan goddess in Greek mythology who gave birth to Selene, the moon, a poetic choice for something that would quite literally give birth to our moon. Theia was a planetary embryo, a world in the process of becoming. Roughly the size of Mars, perhaps 10% of Earth's mass. She'd been forming in a similar orbit to Earth's, gradually accumulating material from the protoplanetary disk, growing larger with each passing millennium. For millions of years, Theia and Earth had orbited the Sun in a delicate gravitational dance, their paths interwoven but never quite intersecting. They shared what astronomers call a Lagrange point, a stable position where the gravitational forces of the Sun and Earth balanced perfectly, allowing Theia to remain in Earth's orbital path without immediate collision. But stability in the early solar system was always temporary, a gradual change in Theia's orbit, perhaps influenced by gravitational perturbat, ions from Jupiter or Venus, perhaps simply the accumulation of small impacts altering her trajectory bit by bit. The change was infinitesimal at first, a few meters per orbit, then a few kilometers, then more. The orbits began to converge. Imagine watching this unfold from some impossible vantage point beyond the Earth-Moon system. Two worlds glowing with internal heat, slowly spiraling toward each other over thousands of years. Not directly, not rushing together, but gradually, inevitably, their paths intersecting at a shallow angle. Theia approached not head-on but obliquely, at perhaps a 30 to 45 degree angle. This detail, this specific geometry, would prove crucial. A head-on collision would have been catastrophic in a different way, perhaps shattering both worlds into fragments. But this glancing blow, this cosmic sideswipe, would create something new. The approach took years, decades perhaps, long enough that if anything conscious had existed on either world, though nothing did, nothing could, it might have watched the other grow larger in the sky night after night, an ominous presence swelling from a bright star to a visible disk to a looming sphere filling half the sky. Slow down time as the final moments approach. Watch Theia's surface in the hours before impact. She's already feeling Earth's gravitational pull, tidal forces beginning to deform her shape, pulling her into an elongated ellipsoid. Her surface, molten and barely crusted, begins to crack and rupture under the strain. Lava wells up through the fractures, glowing bright orange against her dark side. Earth, too, is responding. Tidal bulges form on her surface, the magma ocean sloshing pond. Irisly back and forth, like water in a vast planetary scale bowl. If you could measure temperature from our impossible vantage point, you'd see Earth's surface heating where Theia's gravity pulls hardest, friction and tidal forces adding energy to an already impossibly hot world. The final hour. Theia fills Earth's sky entirely now. You can see the details of her surface, volcanic plains, impact craters from her own formation, rivers of molten rock flowing downhill under her own gravity. Her atmosphere, thin and mostly vaporized rock, is already mixing with Earth's, the two worlds beginning to merge before they even touch. The final minutes. Theia's trailing edge is closest to Earth, the angle of approach meaning she'll strike the young planet with her flank rather than her face. The tidal forces are immense now, visibly reshaping both worlds. Chunks of Theia's surface are being torn away by Earth's gravity, pulled free and drawn into elliptical orbits, some falling back to Theia, others accelerating toward Earth, and then contact. It happens slowly. Not an explosion, not a sudden impact, but a gradual merging. Theia's trailing edge brushes Earth's surface, and where they touch, matter simply combines. Two oceans of molten rock meeting and mixing. The rotation of both worlds, the orbital mechanics, the angle of approach, all of it means this isn't a single moment of impact, but a prolonged collision lasting minutes, perhaps hours. Theia's iron core, denser than her mantle, continues forward with more momentum, plowing through Earth's outer layers like a cannonball through water. But it's not solid, not rigid. It's molten, deformable, behaving more like a very dense lick idea than like solid metal. It shears, fragments, some of it merging with Earth's own core, some of it spiraling outward in the debris cloud that's already forming. The energy release is beyond comprehension. Every second of the collision releases more energy than millions of nuclear weapons. But this isn't an explosion. It's a conversion of kinetic energy to heat, to vaporization, to the melting and mixing of two worlds. Watch as enormous volumes of both planets are simply vaporized, turned into rock vapor, a gas so hot it glows brighter than any furnace. This vapor expands outward, a cloud of superheated silicate and metal gas forming a temporary atmosphere around the merged worlds, stretching tens of thousands of kilometers into space. The collision ejects enormous amounts of material, mostly from Theia and from Earth's mantle layers, the less dense rock that's easier to throw off. This material arcs outward in a great spray, some of it moving fast enough to escape both worlds' gravity entirely, flung into independent orbits around the Sun. But most of it remains gravitationally bound, pulled into orbits around the newly enlarged Earth. The merged planet, no longer quite Earth as she was, not quite Theia, but something new, spins faster now. The collision has added angular momentum, speeding up the rotation. A day on this newly formed world lasts perhaps 5 hours. The surface is completely molten, glowing red hot, an ocean of magma thousands of kilometers deep with no solid land anywhere. Above this hellish surface, in orbit, the ejected material begins to coalesce. Let's drift up now, away from the surface, to watch this next phase unfold. The debris field is enormous, a disk of material extending perhaps 50,000 kilometers from Earth, maybe more. It's a mix of everything, vaporized rock condensing back into liquid droplets, chunks of solid material from both worlds' crusts, molten globs of metal-rich core material, all orbiting the Earth at different speeds and altitudes. This material is hot, some of it is still vapor, gradually cooling and condensing. Much of it is molten, glowing orange and red. The whole debris disk shines with its own light, casting the devastated Earth below in an eerie glow. Now we speed up time, watching days turn to weeks, weeks to months. The debris disk is chaotic at first, particles colliding constantly, sometimes fragmenting, sometimes sticking together. But gradually, patterns emerge. Gravity is sorting the material, pulling it into preferred orbits. Where particles collide, they tend to stick together if they're moving slowly enough. Small clumps form, then larger ones. This is accretion in action, the same process that formed the planets now forming a moon. Within months, perhaps a year, several large masses have formed in the debris disk. These proto-moons orbit Earth independently, each following its own path through the thinning cloud of debris. They continue to grow, sweeping up material from their orbital paths like cosmic vacuum cleaners. But multiple moons are unstable. Their gravity affects each other, perturbing orbits. Over the next few thousand years, the blink of an eye in geological time, these proto-moons either collide with each other, merging into larger bodies, or are flung into new orbits. Some crash back to Earth, some are ejected from the Earth-Moon system entirely. Eventually one body dominates. The largest proto-moon, having consumed or ejected its rivals, sweeps up the remaining debris. The moon is born. She's closer to Earth then than she is now, perhaps 15 to 20,000 kilometers away, rather than today's 380,000. She looms enormous in Earth's sky, 30 times larger than the moon you see today. Her surface is still mostly molten, glowing red-hot, slowly cooling but still radiating the heat of her violent formation. Earth, too, is cooling. The magma ocean begins to form a crust, thin at first, constantly breaking and reforming as convection currents in the molten interior crack the surface open. The planet's faster rotation creates fierce atmospheric currents in the thick vapor atmosphere that's gradually condensing into water. The moon and Earth are gravitationally locked from the beginning, tidal forces so strong that the moon always shows the same face to Earth. But Earth is not yet locked to the moon. She still spins much faster than today, that rapid 5-hour rotation slowly being braked by the moon's tidal pull. Over the next 100 million years, the moon gradually moves away from Earth. Conservation of angular momentum transferring Earth's rotational energy into the moon's orbital energy. She recedes at perhaps 10 centimeters per year initially, much faster than today's annual recession of about 4 centimeters. Earth's rotation slows, days growing longer, the tidal pull weakening as the moon drifts farther away. The moon's surface solidifies, forming the ancient crust that still exists today beneath the younger volcanic plains. She's geologically active for a while, her interior still hot from formation, volcanoes erupting and flooding low-lying areas with basalt. But she's small, and small worlds cool quickly. Within a few 100 million years, her interior has solidified, her volcanism ceased. She becomes the geologically dead world we see today, still bearing the scars of her violent birth. Earth, too, settles into her new configuration. The material from Theia has merged with her mantle and core, enriching her iron content, adding mass and momentum. The collision has completely reset the surface, erasing whatever geological history existed before, but it's also given Earth something precious, a large moon, unusually large for a planet of Earth's size. This moon will prove crucial to Earth's future. She stabilizes Earth's axial tilt, preventing wild swings in climate that might have made the evolution of complex life difficult or impossible. She creates tides that will, billions of years later, shape coastal ecosystems and perhaps even influence the evolution of life, moving from sea to land. She lights the night sky, providing illumination that influences countless biological rhythms. All of this from a collision, from Thea's long fall toward Earth, from that oblique impact, from the debris disk forming and coalescing into the silver sphere that's hung in humanity's sky since our ancestors first looked up and wondered. Rest now in that knowledge. Every time you see the moon, you're looking at the remnant of two worlds merged, at matter that was once part of a planet named Theia, now transformed and preserved in orbit above us. A monument to the most profound collision in Earth's history, hanging serene and patient in the night sky. Let that image settle over you. The moon rising over a quiet landscape, silver and eternal, carrying within her the memory of fire and fusion and rebirth. Breathe slowly. Let your mind drift like the moon drifts across the sky, steady and calm and inevitable. Let's come forward now through billions of years to a much more recent time, to a world where humans walk, where scientists search, where the evidence of ancient collisions lies hidden beneath forests and deserts and ocean floors, waiting to be discovered. The hunt for impact craters is a peculiar kind of archaeology, not of human civilizations, but of cosmic events, a search for scars that the Earth has been slowly, patiently trying to erase for millions of years. Imagine yourself in the Arizona desert, 1902. The sun beats down on a landscape of scrubby vegetation and red-brown earth. You're standing on the rim of a massive circular depression, nearly a mile across and over 500 feet deep. The local ranchers call it Coon Mountain, or sometimes the crater. Geologists of the era assume it's volcanic, an old explosion crater perhaps, or a collapsed magma chamber. But a mining engineer named Daniel Barringer suspects something different. He's been studying the site for months now, examining the strange features that don't quite fit the volcanic explanation. The raised rim, throwing millions of tons of rock outward rather than inward. The fine pulverized rock dust coating everything. The complete absence of any volcanic material, no lava flows, no pumice, no volcanic ash. Most intriguing of all, the fragments of metallic iron scattered around the crater, some weighing hundreds of pounds. Iron alloyed with nickel in ratios that don't occur naturally in Earth's crust. Extraterrestrial iron. Meteoritic iron. Barringer proposes something radical for his time. This crater was formed by the impact of a massive iron meteorite, perhaps millions of years ago. The scientific establishment largely dismisses him. The idea that rocks could fall from space with enough energy to excavate such an enormous crater seems absurd, almost fantastical. But Barringer is patient. He spends years studying the site, drilling exploratory holes, searching for the main mass of the meteorite which he believes must be buried beneath the crater floor. He never finds it. The meteorite largely vaporized on impact, its atoms scattered across the landscape, but his work establishes the fundamental principles of impact crater identification. Let's drift away from Arizona now, forward through the decades. Watch as the science of impact geology gradually gains acceptance. The evidence accumulates. More craters are identified. The understanding deepens. By the 1960s, when humans have begun launching spacecraft and photographing other worlds, the evidence becomes undeniable. The moon's face is battered with craters. Mars too, Mercury, even Venus beneath her thick clouds, reveals circular scars when radar penetrates her atmosphere. Impact cratering is not rare. It's the fundamental process shaping rocky worlds throughout the solar system. Scientists begin to look at Earth with new eyes. If other worlds are covered in impact scars, where are Earth's craters? They must exist, but our planet's surface is dynamic in ways other worlds are not. We have weather, wind and rain eroding rock. We have plate tectonics, continually recycling key crust. We have vegetation covering and concealing geological features. We have oceans covering 70% of the surface. Earth is actively erasing its impact history, but not completely, not fast enough to remove all traces. The craters are there if you know how to look. Let's visit some of these discovered scars, these windows into Earth's violent past. First to northern Quebec, to a landscape of low-rolling hills and countless lakes. From the ground it looks unremarkable, just Canadian wilderness, endless forests of spruce and fir, rocky outcrops smoothed by ancient glaciers. But from the air a pattern emerges. The lakes aren't random, they form concentric rings, circular and precise, centered on a point in the landscape. This is Manicouagan, one of Earth's largest and most spectacular impact structures. The crater itself is over 60 miles across, formed about 214 million years ago when an asteroid roughly 3 miles in diameter struck what was then a very different landscape. The impact released energy equivalent to millions of megatons of TNT, vaporizing the asteroid and excavating a crater perhaps 6 miles deep. Today, the original crater floor has long since rebounded and eroded. What remains is the ring-shaped reservoir, the Manicouagan Reservoir, a vast circular lake surrounding a central uplift that rises as an island in the middle. The water fills the depressed ring formed by the original crater rim and impact melt rocks. Geologists come here to study impact melt, rock that was literally melted by the energy of collision and then solidified again. The Manicouagan impact produced so much melt that it formed a sheet of rock over 200 feet thick. In places, a frozen snapshot of the apocalyptic temperatures generated by impact. Core samples from the impact melt reveal its history. The rock cooled slowly over thousands of years, forming large crystals as it solidified. Within the melt, fragments of the original target rock float like inclusions, pieces that melted partially or not at all, caught up in the maelstrom and preserved. By studying these fragments, geologists can reconstruct what the landscape looked like before the impact. Let's move south now, to the Yucatan Peninsula in Mexico. The year is 1978. A geophysicist named Glenn Penfield is reviewing magnetic survey data collected by Mexico's national oil company. He's looking for potential oil deposits, but something unusual catches his attention. A massive circular anomaly in the magnetic field, centered under the town of Chicxulub Puerto on the peninsula's northern coast. The circle is enormous, nearly 100 miles across. Half of it extends under the Gulf of Mexico. Penfield suspects an impact structure, but the evidence is buried under hundreds of feet of limestone deposited over millions of years. There's nothing visible at the surface, no crater rim, no obvious geological feature. Just this magnetic anomaly and a corresponding circular pattern in gravity measurements. For years the discovery remains obscure, known to a few specialists but not widely publicized. Then in 1980 a physicist named Luis Alvarez and his geologist son Walter publish a revolutionary paper. They've found a thin layer of clay in geological formations around the world, all deposited at exactly the same time, the boundary between the Cretaceous and Paleogene periods, 66 million years ago. This clay layer is enriched in iridium, an element rare in Earth's crust but common in asteroids. The Alvarezes propose that an asteroid impact caused the mass extinction that killed the dinosaurs, and that this iridium-rich clay layer is the global fallout from that impact. The scientific community is skeptical. Where's the crater? An impact large enough to cause global extinction would leave an enormous scar. Where is it? The answer, eventually discovered through the patient work of multiple research teams, is Chicxulub. The magnetic anomaly Penfield found corresponds perfectly to the age and size needed for the extinction-causing impact. Drilling reveals shocked quartz, impact melt, and a crater structure buried beneath the Yucatan limestone. Imagine that impact as it happened. An asteroid perhaps 6 to 9 miles across, traveling at roughly 45,000 miles per hour, strikes a shallow tropical sea. The water offers no meaningful resistance at these velocities. The asteroid punches through the water layer as if it weren't there, striking the limestone and granite beneath. The impact excavates a crater nearly 20 miles deep and over 100 miles across within minutes. The energy release is equivalent to several billion atomic bombs. Rock is vaporized, melted, and thrown into the atmosphere. A fireball expands outward at supersonic speeds, incinerating everything for hundreds of miles in every direction. The impact triggers magnitude 11 earthquakes, far beyond anything in human experience. Tsunamis over 300 feet high race across the Gulf of Mexico and the Atlantic Ocean. Material ejected into space falls back through the atmosphere, heating it to oven-like temperatures and setting off wildfires on a continental scale. But we're getting too dramatic. Let's return to the calm present, to the scientists who discovered this structure, to the patient work of reconstruction. The Chicxulub crater can't be seen from the surface, but geophysical techniques reveal its structure in exquisite detail. Seismic surveys create three-dimensional images of the buried crater, showing the collapsed rim, the terraced inner walls, the central peak ring formed when the crater floor rebounded after impact. Drilling projects bring up cores of impact melt and shocked rock from hundreds of meters below the surface. Each core is a time capsule. The layers tell a story: limestone and other sediments deposited before the impact. Then a chaotic jumble of impact ejecta, fragments of rock thrown out of the crater and fallen back mixed with melted material and shocked minerals. Then above that, the slow return of normal sedimentation as life gradually recovered and the planet healed. Let's visit one more crater, smaller but more recent. We're in Siberia now, in the remote Tunguska region. The year is 1927, 19 years after local residents reported a massive explosion in the forest. An expedition led by Russian scientist Leonid Kulik finally reaches the site. What they find is extraordinary. Trees knocked flat in a radial pattern extending for miles, all pointing away from a central point. But at the center itself, no crater. Just more flattened forest, scorched and dead. This is the Tunguska event of 1908. Not a crater impact, but an airburst. A relatively small asteroid or comet, perhaps 160 feet across, entered Earth's atmosphere and exploded at an altitude of perhaps 5 miles, never reaching the ground intact. The explosion released energy equivalent to 10 to 15 megatons of TNT, enough to flatten 800 square miles of forest. Without a crater, the Tunguska event remained mysterious for decades. Some researchers proposed exotic explanations: a miniature black hole passing through Earth, an antimatter meteor, even a crashed alien spacecraft. But the actual explanation is more prosaic. The object was simply too small and fragile to survive the atmospheric entry intact. It fragmented and exploded in the air, releasing its energy all at once. Studies of the affected area reveal fascinating details. The trees at ground zero, directly beneath the explosion, remained standing, stripped of branches and bark but still upright because the blast wave came down from directly above with no horizontal component to push them over. Moving outward from ground zero, the trees are progressively more damaged, all pointing away from the center. The damage pattern perfectly matches what you'd expect from an aerial explosion. The Tunguska event reminds us that impacts don't always leave obvious craters. Smaller objects can explode in the atmosphere. Larger ones striking ocean don't leave lasting scars on the seabed. The Earth is constantly being hit, but most of the impacts are small, and even the larger ones leave evidence that gradually erodes away. The search for impact craters continues. New structures are discovered every few years, usually not through field work but through satellite imagery, geophysical surveys, or detailed geological mapping. Many are ancient, heavily eroded, barely recognizable. Some buried completely beneath younger sediments, detectable only through drilling or seismic surveys. Each discovery adds to our understanding. The size-frequency distribution of craters tells us about the population of asteroids and comets in the solar system. The ages of craters, determined through radiometric dating of impact melt rocks, reveal the history of impacts over geological time. The chemistry of impact materials helps us understand the composition of the impactors. This is detective work on a planetary scale, piecing together a history written in shattered rock and melted minerals, finding the evidence that Earth tries so diligently to erase. Understanding the role that cosmic collisions have played in shaping our world, from the formation of the moon to the extinction of the dinosaurs to the small but constant rain of meteors that continues today. Rest now in the knowledge that this work continues, that scientists around the world are mapping, drilling, analyzing, that the story of Earth's impacts is still being written, one discovery at a time, that beneath our feet, in the rock itself, the evidence waits patiently to be found. Let yourself drift, like those ancient geologists hiking across the Arizona desert, looking up at the stars and wondering what stories they might tell if only we knew how to read them. The answers are written in stone, waiting in the quiet patience of deep time. Come back now fully to the present moment, to your comfortable room, your soft bed, the gentle darkness around you. Let's contemplate what it means to live on Earth today, protected by invisible shields that render the violence of CE distant and abstract. Every day, without thinking about it, you live beneath a cosmic defense system, not one designed or built, but one that arose naturally from the physics of planetary formation and the chemistry of life itself. A system so effective that you can sleep soundly, never worrying that this might be the night a rock from space finds your particular patch of ground. Consider the atmosphere first, that thin envelope of gases, barely 60 miles deep, seems fragile when you think about it. If Earth were the size of an apple, the atmosphere would be thinner than the apple's skin. And yet it's remarkably effective at protecting us from smaller impacts. Every day, every single day, Earth's atmosphere encounters hundreds of tons of material from space. Most of it is dust-sized, particles smaller than grains of sand. They enter the atmosphere at tremendous velocities, anywhere from 25,000 to 160,000 miles per hour, depending on their orbital path and whether they're catching up to Earth or meeting her head-on. At these speeds, even tiny particles interact dramatically with air molecules. Friction isn't quite the right word. At these velocities, the particles are actually compressing the air ahead of them faster than it can move out of the way, creating immense pressures and temperatures. The particles heat up, begin to glow, ablate away in a trail of vaporized material. You see these as shooting stars, meteors. On a clear night away from city lights, you might see 5 or 10 per hour just by lying back and watching the sky. During meteor showers, when Earth's orbit crosses through debris trails left by comets, you might see dozens per hour. Each one is a tiny world. Ending. A fragment of rock or metal that's been orbiting the sun for billions of years, since the solar system's formation, finally meeting its end in a brief flash of light. Most never reach the ground. They burn up completely at altitudes of 50 to 75 miles, their atoms dispersed into the upper atmosphere, gradually settling as microscopic dust over months and years. The larger ones make it farther. Pebble-sized meteoroids can reach altitudes of 20 or 30 miles before ablating completely. Rarely something basketball-sized survives long enough to explode in the lower atmosphere, creating a bright fireball and sonic booms that rattle windows on the ground below. Very rarely something survives all the way to the surface. These survivors are meteorites, and they're precious to science. Each one is a sample of the solar system, delivered free of charge, requiring no expensive space mission to retrieve. Scientists catalog every recovered meteorite, studying their composition, their structure, their age. Most meteorites are fragments of asteroids, broken off in collisions in the asteroid belt between Mars and Jupiter. Some are pieces of the Moon ejected by impacts and eventually falling to Earth. A rare few are Martian, blasted off the surface of Mars by large impacts and drifting through space for millions of years before Earth's gravity captures them. But the atmosphere protects us from all but the very largest objects. Anything smaller than about 25 meters in diameter will typically break up or explode in the atmosphere before reaching the ground intact. That's the size that caused the Chelyabinsk event in 2013, when a meteor exploded over Russia, injuring over 1,000 people with broken glass from the shock wave, but causing no direct impact damage. The atmosphere is our first shield, our ablative armor, constantly defending us from the small and medium-sized debris that pervades the solar system. Consider now the magnetosphere. You can't see it, can't feel it, but it's there. A vast region of space around Earth dominated by our planet's magnetic field, extending thousands of miles out into space. This magnetic field is generated deep in Earth's core, where convection currents in the liquid iron outer core act like a giant dynamo, creating electric currents that produce magnetic fields. The field extends outward, creating a protective bubble that deflects and traps charged particles from the sun. The sun is constantly streaming plasma outward, the solar wind, a flow of charged particles traveling at hundreds of miles per second. Without Earth's magnetic field, this solar wind would gradually strip away our atmosphere, molecule by molecule, over millions of years. Mars lost most of its atmosphere this way after its magnetic field shut down when its core cooled and solidified. But Earth's magnetosphere deflects the solar wind, channeling it around our planet like water flowing around a rock in a stream. Only near the magnetic poles, where the field lines funnel down toward the surface, do these particles penetrate into the upper atmosphere. When they do, they collide with air molecules, causing them to glow. The aurora borealis and aurora australis, the northern and southern lights, these shimmering curtains of green and red and purple light, are beautiful, but they're also a reminder. They show us where the solar wind would be constantly bombarding us if not for the magnetic field's protection. They reveal the invisible shield that stands between us and the harsh environment of space. Living beneath these shields, you can afford to think of space as distant, abstract, harmless. You can sleep without fear of impacts, walk outside without concern for radiation, breathe air that's been protected from erosion by solar wind for billions of years. But let's contrast this with what life might be like on worlds without such protection. Imagine living on the Moon. No atmosphere at all, no magnetic field. The surface is constantly bombarded by micrometeorites too small to burn up in any atmosphere. Over millions of years, this constant sandblasting has pulverized the lunar surface into a fine dust called regolith. Any human base on the Moon would need to be buried beneath meters of regolith or rock for protection, or shielded with water or some other material. Solar radiation strikes the lunar surface unimpeded. During solar storms, when the sun ejects massive clouds of charged particles, radiation levels spike to dangerous levels. Astronauts on the Moon would need to take shelter during these events. retreating to heavily shielded chambers and waiting for the storm to pass. Even the day-night cycle is hostile. Lunar days last 2 weeks of Earth time, during which the surface heats to over 250 degrees Fahrenheit. Lunar nights, equally long, see temperatures plunge to minus 250 degrees or colder. No atmosphere means no thermal buffering, no spreading of heat from day side to night side. Or consider Mars. She has a thin atmosphere, barely 1% the pressure of Earth's, but it's too thin to provide meaningful protection from radiation or larger meteorites. Has no global magnetic field, just small crustal remnants in some regions, relics of a magnetic field that died billions of years ago when her core solidified. Solar radiation on Mars's surface is far higher than on Earth's. Astronauts living there would need shielded habitats. The thin atmosphere doesn't burn up meteorites the way Earth's does. Impacts are common, and Martian orbiters regularly observe fresh craters forming, dozens each year. Even Venus, despite her thick atmosphere, offers a cautionary tale. Venus has no magnetic field, and over billions of years, the solar wind has stripped away hydrogen from her upper atmosphere. This is one reason Venus is so dry. She may have had oceans early in her history, but the water was gradually lost, the hydrogen escaping to space, the oxygen combining with surface rocks. Earth's shields, atmosphere and magnetosphere, work together to create a uniquely protected environment. An environment where life could evolve in relative safety, where complex ecosystems could develop without being periodically sterilized by impacts or radiation. Think about what this means for the history of life on Earth. For the first few 100 million years, during the late heavy bombardment, life could gain only tentative footholds. Any organisms that evolved would have been regularly destroyed by large impacts. The planet was being sterilized repeatedly, but as the bombardment eased, as the impacts became rarer and less severe, life had time to establish itself, to develop, to spread. Protected by atmosphere and magnetic field, life diversified into countless forms, colonizing every available niche from deep ocean vents to high mountain peaks. The impacts didn't stop entirely. Every few tens of millions of years on average, something large enough to cause global devastation strikes. These impacts have shaped the history of life, causing mass extinctions that cleared out dominant species and allowed new forms to evolve and flourish. The extinction of the dinosaurs is the most famous example, but there have been others. The Permian-Triassic extinction 252 million years ago was even more severe. Estimates suggest over 90% of all species went extinct. While the exact cause remains debated, many scientists suspect impact played a role, possibly combined with massive volcanic eruptions. Each extinction event is a catastrophe for the species living through it, but in the longer view, these catastrophes opened evolutionary opportunities. Mammals, small and relatively insignificant during the dinosaurs' reign, diversified rapidly after the Chicxulub impact. Within 10 million years, a brief time geologically, mammals had evolved into forms ranging from tiny shrews to massive whales, filling ecological niches left vacant by the dinosaurs' extinction. Without that impact, Without that particular cosmic collision, mammals might never have become dominant. Humans might never have evolved. Our existence, in a very real sense, is a consequence of that ancient catastrophe. So we live in a paradox, protected by our atmosphere and magnetic field from constant bombardment, yet shaped by the occasional large impact that penetrates our defenses. Safe enough for life to flourish, but not so safe that we're isolated from the broader solar system's dynamic.
CS.
Consider your daily life through this lens. You wake up in the morning, the sun rising on schedule, the air breathable and clean. You go about your day never thinking about the tons of material burning up in the atmosphere above you, the solar wind being deflected by invisible magnetic fields, the slow rain of cosmic dust settling onto every surface. You look up at the moon, that monument to the largest impact in Earth's history, and see beauty, perhaps romance, certainly not violence. The craters on her face are interesting features to observe through a telescope, not reminders of ongoing cosmic bombardment. This disconnection from the realities of space is possible only because our shields are so effective. They allow us the luxury of thinking of Earth as safe, stable, unchanging. They let us focus on terrestrial concerns, weather and seasons, human conflicts and collaborations, the building of civilizations and cultures. But the protection isn't absolute. Astronomers and planetary scientists maintain watch programs, tracking near-Earth asteroids and comets, calculating their orbits, assessing collision probabilities. Most are no threat. Their paths don't intersect Earth's. But some are classified as potentially hazardous, objects large enough and on orbits that could eventually lead to impact. The good news is that space is vast, orbits are predictable, and we now have the technology to detect threats years or decades in advance. Missions like NASA's DART mission, which deliberately crashed a spacecraft into the asteroid Dimorphos in 2022, have proven that we can alter an asteroid's orbit if necessary. We're no longer entirely passive, entirely at the mercy of cosmic chance. Still, there's something humbling about the knowledge that our safety depends on factors beyond our control. The atmosphere exists because Earth is massive enough to hold on to gases gravitationally. The magnetic field exists because our core remains molten and convecting. These aren't permanent features. They're maintained by ongoing physical processes that could, in principle, change or cease. Mars reminds us of this. She once had a thicker atmosphere, possibly a magnetic field, but her smaller size meant faster cooling, her core solidifying, her magnetic field dying, her atmosphere gradually stripped away by the solar wind. Earth's greater mass gives her a longer lifespan as a protected world, but not an infinite one. Billions of years from now, our core too will cool and solidify. Our magnetic field will fade. Our atmosphere will become vulnerable. But that's billions of years away. A time span so vast it's meaningless in human terms. For now, for the foreseeable future, we live beneath our shields, protected and safe. Rest in that safety now. Feel the air against your skin, the product of billions of years of photosynthesis and volcanic outgassing held in place by Earth's gravity and protected by her magnetic field. Feel the solid ground beneath you, impact-resistant, recycled by plate tectonics, constantly renewed. You are living in the safest era of Earth's history. The late heavy bombardment is long over. The frequency of large impacts has decreased to once every few tens of millions of years. We have the technology to detect and potentially deflect incoming threats. The atmosphere and magnetosphere maintain their protective watch. Sleep soundly beneath us. Invisible shields. Let the knowledge of your safety settle over you like a blanket. The cosmos continues its ancient dance of orbits and collisions, but here, on Earth, you are sheltered, protected, safe. The violence of space is distant, abstract, happening elsewhere or else neutralized by the atmosphere before it can reach you. Breathe slowly. Relax into the comfort of the present. Let the vastness of space and time recede into peaceful abstraction. You are here now, protected by the patient physics of planetary shields that have been operating since Earth's formation, that will continue operating long after you're gone. Rest now. Let sleep come gently, naturally, as inevitable as the moon's orbit, as certain as the atmosphere's protection. Rest.